Hello again, everyone. In this pre-lecture, I want to start talking about the really interesting application of thermodynamics to heat engines. So this had played an important role in the historical development of thermodynamics, and the whole idea of energy is that people were trying to design machines during the 19th century to convert heat into work, and that's the discussion of heat engines. So I want to talk about how to describe those things schematically, what the main purpose of those is, and how to evaluate their effectiveness. So previously we've talked about PV diagrams, all of these different special processes, isochoric, isobaric, isothermal, adiabatic, and we have equations for each one of those and how much work is done and how much heat is added in each one of those. And then we of course have the first law of thermodynamics, which tells us that delta U is equal to Q minus W. So that's just a statement of conservation of energy. And now I want to talk today about heat engines and efficiency. So what is a heat engine? A heat engine is a device which converts heat into work. So heat is the input. For example, on a train, you take coal and you put it into the fire, you burn it, that creates heat, and then you use that heat to do something, which in this case is getting the engine to run. So the input is heat, the output is work. And this is like kind of a schematic diagram that you'll see these kinds of things over and over again. The engine, the thing which is doing that conversion, is this thing, this green circle here. And the input is heat, the output is work. And then there's some other output, which is sort of heat, which is not perfectly converted into work, sort of left over in that conversion process, which is what we call Q out. That heat is exhausted to what we call a cold reservoir. So here's the schematic diagram of the engine. Let me say a few more things about it. Okay, so a heat engine is a device which converts heat into work. Okay. If you want to convert work into heat, that's easy. That happens all the time. If I slide a book across the floor, it will eventually stop. I put work into it to get it moving. It'll eventually stop. Where did the energy go? The energy went into heating up the floor and the book. The work that I put in when I slid the book across the floor gets converted into heat very easily. We see that happen all the time. Something that goes the other way, which converts heat into work, is a little trickier, and that took people a little bit longer to figure out how to do that. So here's my schematic diagram. Q in is the input. Work is the output, and then also there's some waste heat, Q out, which also is output. The engine takes the heat input from something called a hot reservoir. So let me make sure you understand what this means. So reservoir is a very large source of heat, let's say. And it has a temperature TH. So the hot reservoir has temperature TH. So that's going to be the thing that provides the input of heat. And then Tc will be the temperature of the cold reservoir. I should make clear, it doesn't have to be hot and cold. It just has to be one is hotter than the other. So Th is larger than Tc. Okay, it doesn't, one of these could be 0 degrees Celsius, and one of them could be 10 degrees Celsius. We would say both of those are pretty cold relative to, human body temperature, but I can still call one of them the hot reservoir and one the cold reservoir. Okay. And one other important thing to notice about the reservoir is that I'm assuming it's really large. The reservoirs always remain at the same temperature. Okay, so I think about it, it's something that's so big that I can take some heat out of it, but its heat capacity is so large that its temperature won't change very much. In other words, CV is very large. Think about it like Lake Ontario. Lake Ontario is a huge, giant source of heat. So it's a huge body of water. If I took some energy out of Lake Ontario, its temperature wouldn't change very much. Or relatedly, if I dump a cup of hot water into Lake Ontario, its temperature doesn't change in any significant way. Okay, it's so large, its temperature doesn't change in any appreciable way. So those temperatures of those reservoirs are fixed. Okay, so now we've got our input is heat, and we call that Q in, and the output is work plus, I'm going to call it waste heat if you want. It's heat that was not perfectly converted into work, or it's some exhausted heat or something like this, right? So it's W plus, and this is Q out, okay? Let's assume the engine runs with using a closed container of ideal gas. And the other thing that's important to know is that the engine should be cyclical. So I want my engine to be cyclical. I want to be able to run it over and over again. Okay, so I want it to do something and then return to its initial state so I can do that thing again, over and over again. I want to constantly be able to convert heat into work. So here's one simple example of an engine. So let's take a look at what happens here. Suppose I start here. In this container is the ideal gas. So I've got some gas molecules in there. And I've got a weight on top of the pistons as the usual setup, so the piston is able to move up and down. So let's say I add some heat, and the heat is being added at constant pressure, right? So this is an isobaric heating. So the piston is able to expand up and down. So as I add the heat, the volume will expand, keeping the pressure constant as the temperature goes up in the ideal gas, okay? So that's where the gas is doing work. It's expanding, pushing that mass upward, that is doing work. Now maybe when it reaches the top, I have a pin which I can lock the piston in place here, okay? And then I can remove the mass, let's say. And then while this is going on, I take it off of the heat, and so I let it cool back down. Okay, so now I have constant volume cooling. So this is isochoric cooling. The volume is fixed because I locked the pin, and the heat is going out of the gas into the environment. So I'm exhausting some heat here. And then at some point I will unlock the pin, and then I will push the piston back down with some external force here to get it back to where it started. So this is a isothermal compression. So it's in contact with some, something cold, let's say water. And then I push it back down. As I push it down, more heat flows out of it until it returns to its initial position. So that's isothermal compression. This is just one possible example of a heat engine, okay? There's many cycles I could do. This is just a simple one to imagine. And then once I'm here, now I've gone back to my initial state. Now I just go back here, put the mass back on it, and do it again. Every time I do this cycle, I get some work out of the gas, right? The gas has expanded and lifts up that mass. That does some work. And then I have to do some work here to push it back to its initial starting place. So let's think about, how do I represent this on a PV diagram? So let's call this state 1, and let's call this state 2, and let's call this state 3, in between here. Okay, so let's say I start off at some state 1 here. Okay, so 1 is going to be there. And then I add the heat at constant pressure, right? Isobaric heating. So this is going to be 1. Now I'm adding the heat in until I reach, let's say, some point here. And this will be state 2. So that's going to be the maximum volume that the gas reaches, and that's when I lock the pin in place. Okay. So you can see the gas did some work during that time. The work done would be equal to the area underneath this curve here, which you know how to calculate. Okay, now once I reach state 2, I'm going to take the mass off of it and let the gas cool back down to a lower temperature. So I will let it cool back down to, let's say, here. So this will be state 3. And I'm going to choose it so that the temperature of state 3 is equal to the temperature of state 1. Okay, so now I have constant volume cooling. That's what's going on here. And then isothermal compression, I'm going to push the gas down, keeping it at the same temperature. So the temperature of 3 is the same as temperature of 1. So something that looks like that. So that's my isothermal compression. Okay, so temperature of 3 is equal to the temperature of 1. Okay, what's going on here? Where's the heat being added? We usually represent it like this. Heat is coming in here. So this is what I'm going to call Q in. When I go from 1 to 2, that's my heat going in, right? Now, where is heat going out? In 2 places, actually. So there's a Q out here, so let me call this Q23. And then there's another Q out here, which is Q31. Okay. So the heat's coming in between 1 and 2, and then the heat's going out between 2 and 3, and then also between 3 and 1. Okay, where's the work being done? The work is being done between 1 and 2. Work from 1 to 2 is positive, right, because the gas expands. Now, when I go from 3 to 1, the gas is contracting, so the work from 3 to 1 is negative. The gas is compressed. So I got some work out of it from step 1 to 2. I put some work into it from 3 to 1. But which is bigger? This one is bigger than this one, right? Because the area underneath the curve from 1 to 2 is bigger than the area underneath the curve from 1 to 3. So the gas expanded and did some work. I had to put some work into it in order to push it back to its initial position. But the amount of work that I needed to do is less than the amount of work that the gas did. Okay. So I got some net work out of it. W1 to 2 plus W3 to 1, let's call this the net work, is positive. How is that possible? How did I get net work out of it? Where did that energy come from? It came from the addition of the heat, right? So I took some of the heat in order to do some work, and then I exhausted some heat out. So I should say that Q in is equal to the heat added between 1 to 2, and then Q out is the sum of these two, 2 to 3 plus 3 to 1. Okay. So that's an example of a simple engine. It's a cyclical process. It goes, you can do this many times, over and over again, and every time you do it, you take some heat in from this hot reservoir, and then you do some work, and then you exhaust some heat into this cold reservoir. Okay. Let's think more generally now about heat engines. So let's use the first law of thermodynamics. Delta U is equal to Q minus W. Okay, so in one cycle, U final is equal to U initial, which means that delta U is equal to 0. In other words, the gas always starts at some place and then ends up back at the same place if it's a cyclical process. Okay, so it'll start at 1, do something, and then end up back at 1. So U final is equal to U initial, and delta U is equal to 0 for the gas. And that means that delta U is equal to Q minus W, so this is going to be 0. Remember that Q is the heat added to the gas, and W is the work done by the gas. So remember, Q equals heat added to the gas, and W is work done by the gas. So this is like the net work and the net amount of heat added to the gas. So I'm going to do it like this. It's going to be Q in plus Q out, because the heat might be added and also exhausted, minus W. And so I get this relationship that Q in plus Q out is equal to the work done by the gas. Now, be very careful about the sign conventions. Remember, Q is positive if heat is added to the gas. Q is negative if the heat is removed or exhausted from the gas. Okay. So Q in will be a positive number. This is positive. Q out will be negative. And hopefully W will be positive, because otherwise your engine is not worth anything if it doesn't have any positive work being done. Okay. So this is just an expression of conservation of energy here from the first law of thermodynamics. Now let's talk about the efficiency of the engine. How good is it? I want to know, how good is it at its job of converting heat into work? Efficiency is defined by this Greek letter eta. It's what you get divided by what you pay for it. So what you get divided by what you pay. So what you get is work. That's the whole goal of this thing. So that's what I'm getting out. And what I pay for it is heat in. Okay. I can write this using the equation above as Q in plus Q out over Q in. Now remember, Q out is a negative number. So maybe I should write this in a more obvious way. Let me write Q out is equal to minus the absolute value of Q out. So I'm going to put the minus sign there explicitly, reminding myself that Q out is a negative number. So then my efficiency is 1 minus Q out over Q in. What are the possible ranges of values that eta could run between? It will run between 0 and 1 based on energy considerations. So eta equals 0, with the efficiency equal to 0, means I get no work is done. What would that look like in my engine diagram? That would be like some hot reservoir and some cold reservoir, and my engine wouldn't do anything. It would just transfer heat from the hot to the cold. So that's a pretty useless engine. Work done is 0. Eta is equal to 0. What would a perfectly efficient engine look like? Eta equals to 1 would be something that looks like this. Basically, my input is, what I get is work, and what I pay for it is heat, and those two things are exactly the same. So that would be something like this. Take in the heat, output the work, and don't exhaust anything, right? So if if the heat is perfectly converted to work, then I would have a perfectly efficient engine. We will talk about later on that this is impossible. This is actually impossible. And we'll talk about why. But based on the first law of thermodynamics, it seems like it should be possible. Energy is conserved and converting heat into work. But in real life, that's not actually possible, and we'll talk about why. Hopefully it's clear that you can't have efficiency bigger than 1, because that would mean that I would be creating more work than I got in, and that's not possible, right? That's a violation of conservation of energy. Eta bigger than 1, W is larger than Q in, which means that energy was created by the engine, which we know is impossible, violates conservation of energy. Or in other words, it violates the first law. So this is not possible. So based on just the first law alone, I should expect my efficiency to be somewhere between 0 and 1. 1 would be like the ideal, perfect engine. 0 would be a useless engine. A real engine would be somewhere in between. Let me summarize what we talked about. So I explained to you the basic idea of a heat engine, something which converts heat into work. I gave you a simple example of a heat engine. So this is a cyclical process. It's got to form a closed loop in the PV diagram. The one that I did here was it had isobaric heating, isochoric cooling, and then isothermal compression. But any diagram that I create which forms a closed loop in here could be a heat engine. We talked about energy considerations in the heat engine. So basically, the energy in is equal to the energy out. Based on the first law, Q in plus Q out is equal to work. In other words, no energy is created or destroyed in this process. And then we talked about the efficiency of the engine, which is what you get divided by what you pay. That's the work done by the engine divided by the heat you put into it. And you can use this equation above to write it in terms of the heat out and the heat in. Okay? If there's no heat output, my engine would be perfectly efficient. If my heat output was equal to my heat input, my engine would have 0 efficiency and wouldn't be doing any work. Okay. So we'll leave it there, and we'll do some more examples of calculating the efficiency of particular engines when we pick this up in class. Thanks again for your attention. See you all then.